So the purpose of this lecture segment is to give some examples of linear recurrence relations which don't have constant coefficients, but which have a useful application. And the application is to counting derangements, which are special types of permutations. So I want to consider a permutation of n objects, which is convenient to label as the numbers, the integers 1 up to n. And the permutation is said to be a derangement if it moves every single number. So no number is left fixed. One could say there's no fixed point. So one can say that in a positive way to say that the absolute value of the image of I minus I is positive, strictly positive for every number I. That's the definition of a derangement. Now the question is, how many derangements are there for given fixed n? So we know that there are n factorial permutations. Let dn be the number of those that are derangements, that move every single number. So in particular, if n is 1, the number's got to stay fixed. There's no choice. That's not a derangement. So d1 is 0. But if we have two numbers, then either they stay the same, that's the identity permutation, or they're swapped. If they're swapped, that's a derangement. So d2 is 1. What about d3, when we have three numbers? Well, here you can use the description of permutations that one often does in group theory. So one knows that a permutation can be written as a product of disjoint cycles in an essentially unique way up to the order. So here I've exaggerated the notation a bit to emphasize the numbers that don't change. So there's the identity permutation. You would normally write that as E or ID or something, but that just means where each of the three numbers stays fixed. That's obviously not a derangement because they're all fixed. Then there are the two cycles, which are these permutations which just swap two of the three numbers and leave one the same. Those are not derangements because one's being left the same. Normally we don't bother to write these things that stay the same. We just have the two cycles. They're not derangements. But the 2-3 cycles are derangements because no integer stays fixed. So d3 is 2. And you can proceed like this if you know the different ways of writing. For example, if n is 4, you can write the different ways of writing permutations with 4 numbers. Really corresponds to conjugacy classes in the group, if you've studied that. And the only derangements come from the double transpositions. That's something like swapping 1 and 2 and 3 and 4. There are 3 of those. And the 4 cycles, in which the 4 numbers are cyclically permuted, and there are 6 of those. So actually d4 is 9. But it gets pretty laborious to do this using the group theory, so one needs a more combinatorial way of finding the formula for dn. And that's really the point of what I want to talk about. So, but before I give you the result, let me say that actually it would be more natural to try to study the ratio dn divided by n factorial. That's the proportion of permutations which are derangements. Or if you like, it's the probability that choosing a permutation at random, like shuffling cards, is a derangement. And in fact, I'll show you at the end of the talk, with cards, virtually, that we can, actually it's not going to work, but in theory one can do the experiment and see if this bears out the value of dn we're going to find. So the point is that if we choose the permutation at random, that's like taking a shuffled deck of n cards and laying them out in a row and seeing whether one or more cards remains in its correct position. but we'll see that later. Okay, so here's the key result. So this is, I'm going to give a theorem with 3 parts. This is actually the 3rd part in the lecture notes, so I've labelled it part 3. And it's quite easy really to remember this, namely this ratio dn over n factorial is the alternating sum of these reciprocals of factorials. So if n is even, it will go up to plus 1 over n factorial. If n is odd, it will go up to minus 1 over n factorial. And you should recognise this as the terms in the series for e to the power minus 1. If you think of e to the x and put x to be minus 1, you'll get this series. So if we take n to be larger and larger, in the limit, the sum is 1 over e. Actually, this series converges extremely quickly to 1 over e. So even when n is relatively small, this ratio is almost exactly 1 over e. If you take n to be 7, you actually get 1 over e correct to 4 decimal places. And that would correspond to playing around with a deck of 7 cards. If you had 52 cards and shuffled them and used them to determine a random permutation, you'd actually get a probability that equals 1 over e to, I think, 69 decimal places. Accurate to 69 decimal places, which is incredible. Anyway, the first and second parts of the theorem are these 2 recurrence relations which I've written, namely this one and this one. So it turns out that this number dn, which is given by the formula at the top, the formula at the top of the page is the easiest to use to work it out. But in order to prove that formula, one typically, first of all, proves part 1 here, and then one easily deduces part 2. And part 2 is very, as you can see from the minus 1 to the n, you just divide, if we divide both sides of part 2 by n factorial, we quickly get this formula here. So I'm not going to prove part 1, but I will show you how you can deduce part 2 from part 3 and refer you to the lecture notes for understanding part 1. I just want to point out that these recurrence relations, they are linear recurrence relations. If you look at the first one here, we have dn is a linear combination of the 2 preceding terms in the sequence, dn minus 1, dn minus 2. This is a recurrence relation of 2nd order, and it's homogeneous because there's no additional term. Whereas the second recurrence relation, it's nicer in one sense because it's a 1st order recurrence relation. It's very neat actually, but it's non-homogeneous because of this extra term minus 1 to the n. So you can take your pick which one you prefer, but in any case, to make these work also for initial values of n, we typically define d0 to be 1, even though it has no real meaning in terms of permutations. So let me just then say that, as I say, one can prove that 1 implies 2, 2 implies 3, and what I didn't say here is that in the lecture notes we prove 1. So I'm actually going to do now the proof that 1 implies 2, hopefully. Now let's just pause just to look at the 3 formula again. So number 1, here we are, number 1, 2nd order recurrence relation. Number 2, which is a somewhat neater 1st order recurrence relation, very similar to the recurrence relation defining factorials. If this term were not there, then it would just be the recurrence relation that defines factorials. But we know that dn is sort of related in some sense by its definition to factorials. And in fact, to get dn rather than n factorial, that comes about by the addition of this extra term minus 1 to the n. And then this quickly leads to this formula involving the series for e to the power minus 1, or the reciprocal of e, 1 over e. Okay, so I just want to go through the proof, and it's actually rather elementary that the first recurrence relation implies the second one. So to do that, let's just, let me set an to be dn minus n times dn minus 1. Okay, so if we just go back a moment, you see that dn minus n times dn minus 1, that's now minus, so I can put a minus sign there if you like, and then this is equal to minus 1 to the n. That's the same relation. So we want to show that an is equal to minus 1 to the n. That would be the second relation. So we want to show that, having defined an to be that, I want to show that an is minus 1 to the n. How do I do that? Well, let's first of all remark that because we know what d1 and d0 are, a1 is minus 1, because a1 is d1, which is 0, minus 1 times d0, which we define to be 1, so it's minus 1. And we have to show that, as I've said twice before, an is minus 1 to the n. Well, this is very easy because we use the first relation, the first recurrence relation is this one here. It's this, I've taken out the common factor of n minus 1. It's even clearer. This is a second order linear recurrence relation. And then we simply put the n times dn minus 1 on the left hand side. So that gives us the an. And we're left with minus 1 times dn minus 1, this term. And then the second term stays the same. But you see, this expression here is exactly minus the definition of an minus 1. You look at this and replace n by n minus 1, change the signs, you'll get precisely this middle expression here. So we actually get a recurrence relation for an. I'll just write it for emphasis here. Namely, an is equal to minus an minus 1. So in other words, the sequence an is just swapping signs. We know that a1 is minus 1, so that tells you that an has to be minus 1 to the n. So that's finished it. The proof's that straightforward, deducing the second equation from the first equation. So I've just repeated here what I've just said. An, you can even use the theory of recurrence relations if you like. You can say, well, this is first order recurrence relation. We find the root's going to be minus 1, so an has to be a constant times minus 1 to the n, but that constant has to be minus a1 if you think about it. And so a1, so in other words, we get minus 1 to the n. So maybe that was a bit quick here. Why is this true? Well, if you put n is equal to 1, then you'll get, we want to get a1 is equal to a1. So that's correct. That's what the constant is. And so we get an is minus 1 to the n. Now it's very easy to use this formula, the second recurrence relation, to compute higher values of dn. So remember, d4 we already showed was equal to 9. You could even check that from d3, but if you know d4 is 9, you get that d5 is 5 9s 45 minus 1, that's 44. d6 is 6 times 44 plus 1, which is 265 apparently. And d7 is 7 times 265, this should be, minus 1, which I think with this correction is 1854. And I know that's right because I worked out d7 divided by this d7 divided by 7 factorial, and again this comes out to equal 1 over e, correct to 4 decimal places. Okay, so that's the theory. Remember that dn over n factorial is roughly 1 over e, even for quite small values of n. That's about 0.37, just a bit more than a third. So that should correspond to the probability that when you draw cards, you don't get any coincidence. So you should get coincidences very roughly 2/3 of the times. And we're going to look at that now and see whether it bears out in practice. So we've come now to the experimental part of this talk. And what I've effectively done here is to choose a deck of 10 playing cards, numbered from 1 to 10, shuffled them, and laid them out in a row, all virtually, of course, using this website, random.org, developed by Mass-Ha at the Trinity College Dublin. And I'm grateful to Dr. Ha for allowing me to use this site, which seems tailor-made to this particular exercise. Anyway, what we have here is effectively a permutation because we can compare the position of the card with its value. So in this particular deal, you see the 4 of hearts is occupying its correct position, as is the 10 of hearts at the end of the row. So we have two cards, which, if you like, two coincidences, cards in their correct position. So this is not a derangement. We can think of this row of cards as a permutation in which the number 1 is mapped to 5, the number 2 is mapped to 3, and so on. So I'm going to keep drawing the cards, and we'll take a tally of whether or not there is a derangement. So let's draw again. One, I have to count carefully not to make a mistake. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is no coincidence, so that does count as a derangement. So none means the permutation is a derangement. Once again, 1, 2, 3, 4. 4 is again in its correct position, so this is there is at least one coincidence. So the permutation is not a derangement. Incidentally, if you want to do this with actual playing cards, it's more fun to have 2 decks of cards, each deck with the same number of cards, maybe 10, 20 or 52. Then you shuffle both decks, put them face down on the table, and draw 1 card from each deck simultaneously and compare them. And if you get a coincidence or snap, you stop. And that's really the same thing, because to shuffle both cards is like just shuffling one. To shuffle both decks is like shuffling one deck and leaving the other deck with the cards in their natural order. So defines a permutation. Anyway, let me go on and draw again. Try and be a bit quicker now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No coincidence. Again. 1. Coincidence with the ace. 1, 2, 3, 4, 5, 6, 7. Coincidence with the 7. 1, 2. Coincidence with the 2. I don't bother if there's... I only need 1 coincidence. There may be others, but I don't care. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No coincidence. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No coincidence. So it's 4 all, actually, at the moment. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The derangements are winning, which is not quite what the maths predicts, but it should even out in the long term. 1, 2, 3, 4, 5. Coincidence with 5. 1, 2, 3, 4, 5, 6, 7, 8. Coincidence with 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. no coincidence, I think. It's easy to get an error when I do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 and 9 have been transposed, but it's no coincidence. 1, 2. 2 is in its correct position. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No coincidence. So again, it's not quite going the way I'd hoped. 1, 2, 3, 4, 5. Coincidence. So what are we? 8 all now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No coincidence. 1, 2. Coincidence. 1, 2, 3, 4, 5, 6. 6. Coincidence. 1, 2, 3, 4. Coincidence. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No coincidence. 1, 2, 3, 4, 5, 6. Coincidence. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No coincidence. Well, that's not quite what I expected, but I have to stop there, to be fair. I can't fiddle this. So you see, we've got a total of 12 coincidences and 11 derangements. 12 permutations, I should say, in which there's one or more coincidence, and 11 derangements. So it's almost 50-50. It's not quite the percentages we expect from the maths we did earlier in this talk. But that's the way things go. I can assure you that the website is a true random generator. Apparently it's based on atmospheric noise. And I invite you to see whether you can do better than me.